And we have our step one. We have the fourth step again. Step one is going to be to name the parameter and give what are called our hypotheses. So what I'm going to write for my step one is that we got this population mean, that's our parameter, mu, and that's going to be the average chocolate chips per cookie by Chips Ahoy. Okay, and the hypotheses, we got two hypotheses. First, we have what's called a null hypothesis. H-E-S-I-S, which I abbreviate H sub 0 or H sub O or H sub naught. And the null hypothesis is about there being no change from the claim amount. So, no change. Oops, that's horribly written. Action. Tools. There we go. Tool. Eraser. Sorry. I don't know where my toolbar went. Pen. No change from claimed amount. And we'll write that symbolically, that H sub 0, our null hypothesis, is that the mean of this population is equal to what they claimed, 25 chips. And I'll give units here. And then we have an alternative hypothesis. And that one we call H sub A. And that one is about the claimed amount not being true. So, and we'll write that one symbolically. H sub A equals mu is not 25 chocolate chips. Okay? And our step two, we will name our procedure, which means we will, we're not doing a confidence interval this time, we're doing a significance test. We're either doing this on a population mean or proportion. This is for a population mean. What distribution we're going to use this time? We'll use the T. And we have one sample. Okay, so that's good enough in naming our procedure. And then we check conditions. And the conditions we need to check are the same kind of conditions that we did for confidence interval, SRS, normality of sampling distribution, and independence. And of course, did we do a simple random sample of chocolate chips from Chips Ahoy? No, we didn't, so we haven't met conditions. Normality, we got normality because we had our sample size was greater than 35, and so the central limit theorem kicks in and we get normality of our sampling distribution, or approximate normality of our sampling distribution, so we're good. And independence, boy, we didn't get even a random sample here, so so we won't meet independence either, but it doesn't really matter. Because we didn't get a simple random sample, so we should just kind of stop our analysis right here. But let's Let's not. Let's say we had these things. And then step 3 is to do the math. And the math will get a test statistic. That was that t. That was the sample mean minus the hypothesized mean divided by the standard error of the mean. And we got that to be 5.8. And then we have something called a p-value. And the p-value is the probability, B-A-B-I-L-I-T-Y, there we go, is the probability we get a sample mean this far or even further from our hypothesized mean. That'd be mu. And what was that probability? Oh, well, that p-value was 0. Which means it's very rare. So we'll go into the interpretation of that a little bit more tomorrow. Let me just give you some caveats, some warnings right now. Null hypothesis will always have an equals to it. When I learned stats back, my first stats class way back when, you didn't use equals all the time, but now we do. Oops. And the alternative hypothesis will always be either not equals, greater than, or less than. And these are always about population parameters and never the samples are mentioned in the hypotheses. More tomorrow.